Okay, we can just get started on the next talk. Okay, so higher order abstractions, what is that? So actually, I'm really just going to talk about some type classes in Haskell. Of course, this is not really specific to Haskell, but these are some type classes that you'll see in Haskell, maybe. Actually, this is just going to like lead up to Profunctor. So if you already know what Profunctor is, then you probably won't get much out of this talk. All right, let's begin. So let's review what Functor. Everyone, I think, knows what Functor is. Functor just is a type class that classifies types which can be mapped over. So Functor supports a function called fmap, and fmap takes a function from A to B, and then also an FA, and it converts it to an FB. So what is F here? F is a type constructor, so it could be something like list or maybe or something like that. And type classes, well-behaved type classes, satisfy laws. So the laws for Functor are here, and you can reason about Functor using these laws. Okay, so these pictures I think will be helpful for the more advanced type classes that we're going to talk about in a minute, so bear with me. I think of a Functor as a container. Of course, we know that not all functors are literal containers, but it's a kind of a good mental model. So a functor that contains A's, when given a function from A to B, kind of gives you back a thing that contains B's. Okay, it's pretty straightforward. All right, so there's the definition of functor that we saw before, and here's some examples. So we see that lists are functors, or I should say there's an instance of functor for lists. Same for maybe. And at this bottom, so this, I don't know if you can read this syntax if you don't know Haskell. But this arrow thing, that's just function arrow. And it's like we're partially applying it on the first, which is the argument type. So we're fixing the argument type to be some type R. And then it's the return type is like free. And we're saying that it's functorial in that type. Okay, so let's talk about Bifunctor. Which is kind of a trivial extension of Functor to have two type parameters instead of one. Okay, so Bifunctor will take, so it has a function called ByMap, which is a lot like fmap, except that it takes two mapping functions. It takes a function from A to B and a function from C to D. And so P here is a bifunctor, so P of AC is what you're starting with, and then what you end up with is a P of B and D. And of course, bifunctors have these laws. So let me give some intuition for how bifunctors work. So if we have a container that contains like maybe some mix of A's and B's, or maybe it just has A's, but it could also have B's. And I also have a function from A to C, and I have a function from B to D. Then ByMap will give me kind of a container that gives me C's and D's, or a container that contains C's and D's. So here are some examples of bifunctor. So pair, so tuple is, well, the obvious example that comes to my mind. It's functorial in the first and the second element in the tuple. And either is also a bifunctor. That's pretty straightforward. All right, so this is where we get to the more like counterintuitive stuff. Contravariant is kind of like it's like functor but backwards. So here's the definition of contravariant. Contramap is a function that looks a lot like fmap, right? It takes an A to B function, right? But then what's this? Then we take a FB and we return an FA. How do we get the FA? It's like we have to apply the function backwards? Like, what? Let me illustrate this with pictures. I think a picture speaks 1,000 words here. So really, we think of this thing as not a container of A's or B's, but it's really a thing that's hungry for B's. Maybe a function that takes a B as an input. And then we give it a function from A to B. And what that means is we're actually going to call the function first. So we start with an A, we call the function, get a B, and then we feed the B into the hungry B eater machine. And then that gives us something that's hungry for A's. So that's how contravariant works. So this is contravariant functor, that's what it means. Which means that the ordinary functor type class is covariant. Okay. Contravariant is pretty weird, so let's talk about some concrete examples. So the most common one, I think, is a predicate. So predicate is just a function which returns a Boolean. That's all it is. So, but what's the argument type? Well, it's not specified. It's just, for all types A to bool, that's predicate. Okay, so a predicate is contravariant. You can think of it as like, you know you're going to end up with a bool, and you have to give it an A. But if you have a function that takes B's and returns A's, you could call that function on a B, get an A, and then feed it to the predicate. So that's how the contour map works here. So this F, when composed with the predicate, but in this direction, so it's kind of like F runs first, and then the result gets fed into P, the predicate. So that's how you contour map over a contravariant function. Cool. Okay, so this is like a pop quiz for the audience. So I have a list of types here. Some of them are going to be, they're going to have functor instances, and some of them will have contravariant instances in terms of this type parameter A. Okay, so let's just do the first one together. So if I have a function from int to A, can I make a functor instance, or can I make a contravariant instance, or both, or neither? Does anyone know? Functor, of course, yes. So it's covariant. All right. What about A to int? Well, that's the example we gave just a second ago, so that's like, it's obviously contravariant. Okay, what about this next one? Int to A, and then the whole thing to int. Also contravariant. Good, okay. This next one? Yes, covariant functor. Okay, how about this one? It has A's, it has two A's. Does that matter? So this one is kind of I was tricking you. Oh, sorry, yeah, that one was contravariant. Okay, so A to int. Yeah, this one is contravariant. That's weird, right? Is that surprising to anyone? No, it's not that surprising. Because both the A's appear in negative position. I'll explain what that means in a second. What about number 7? So this one, we have an A in negative position and an A in positive position. I heard a covariant and a contravariant. It's actually invariant. It's neither. You can't make a functor instance for this, and you can't make a contravariant instance for this. If you try for 1,000 years, it would not work. Okay, what about the last one, phantom A? So this A type parameter is not even used in the type. It's a phantom type variable. So this one we say is bivariant. It's actually, you could make a covariant, a functor instance, or a contravariant instance. So the trick, so how do you know? So the trick is like you basically just check, okay, how many arrows is A to the left of? And if it's an odd number, then you have contravariant. If it's even number, then it's covariant. So basically, you're looking at how deeply nested is the A. That's all. It's an easy trick. Okay, so let's talk about Profunctor, because this is the really magical one. Profunctor has a function called ByMap, and this looks a lot like Bifunctor, because it takes two functions, A to B and C to D, and P, B, C. But this is kind of weird because, okay, so B is like the return type of the first function, but C is the argument for the second function. So what's going on here? So this thing is actually contravariant in the first type argument and covariant in the second type argument. That's weird. So let's have a picture. Okay. So you can think of a Profunctor as something that's hungry for B's, and it also contains C's. And if you give it a function from C to D, and you also give it a function from A to B, then, well, we get this whole thing which is hungry for A's, because you could just take an A, feed it through the left function, and then you get the B that it wants. And it also contains D's because, well, it really contains C's, but then you could always call the function on the right to get the D. So it's kind of like we've extended it in both directions. And that's the power of Profunctor. Anything where you can just like extend do this mapping in both directions, that's the Profunctor. So we can talk about some examples. So function arrow, this is a good example. This is kind of trivial. You just compose the functions, f, g, h. Lens and prism, so who knows what Profunctor optics are? Anyone familiar with these terms? Most of you are not. Okay. Well, if you want to learn about Profunctor optics, Profunctor is the prerequisite knowledge. And so now you have it. Okay. That's it. That's the time.